This is another database question. The reason for a second database question is for two things. The first is that this has an IVT justification versus the last one, which had an MVT justification. Then there's also a related rates component to this problem. The first thing says find the average acceleration. So the average acceleration, what people would commonly do wrong here is they would try to find the acceleration at 8 and the acceleration at 2, and they would try to subtract that, but the average acceleration is going to be the change in the velocities over the change in time, which gives us units for acceleration. So from 8 to 2, the velocity at 8 is negative 120, minus the velocity at 2, which is 100, over 8 minus 2. There is our average acceleration. This is free response, so no need to simplify. This question is also not calculated. Part B is our IVT justification. What they tell us is that V sub A of t is a differentiable function. They ask us if the train's velocity will ever be negative 100 between 5 and 8. The velocity at 5 is 40. The velocity at 8 is negative 120. So since V sub A of t is differentiable, V sub A of t is continuous on the interval that we're interested in, which is 5 to 8. With V sub A at 5 being greater than negative 100, which is greater than V sub A of 8. So just saying that the y value that we're interested in, or the velocity value that we're interested in, is in between the velocities of the endpoints of this interval. So we have our conditions. This inequality is our analysis. Our conclusion, which is what the question was asking us to prove. So there is a t in the interval from 5 to 8 where V sub A of t equals negative 100, which is the velocity value that we're interested in, by IVT. Conditions analysis conclusion theorem. Part C tells us that train A's position is 300 meters east of origin station. The train is moving east. Write an expression involving an interval that gives the position of train A at time t equals 12. If we integrate the velocity from 2 to 12, that'll give us the change in position from 2 to 12. So x of 12, x sub A of 12, minus x sub A of 2. This is first fundamental theorem because VA of t is x prime A of t. So integrating the rate of change of x gives us the amount of change in x. And then it says use a trapezoidal sum with 3 subintervals to approximate the position at time t equals 12. We could also write this as x sub A of 12 is equal to x sub A of 2 plus this interval from 2 to 12. And then we're approximating that integral with the trapezoidal sum. So if we're approximating the integral, then we must also be approximating the value of x sub A of 12. They also tell us that x sub A of 2 is 300. So 300 plus the trapezoidal sum, that is this integral. Might need more space in this. 1/2 base 1 plus base 2 times the height, plus 1/2 base 1 plus base 2 times the height, plus 1/2 base 1 plus base 2 times the height. So 3 trapezoids from 2 to 12. Here's the first one from 2 to 5, the second one from 5 to 8, the third one from 8 to 12. The bases are the velocities. So the first one is 140 are the first two bases, and the height is the change in the time, so 3. And then 40 and negative 120 are the height of that trapezoid, another 3. And then the last trapezoid, negative 120 and negative 150. And then from 8 to 12, which makes 4. This is free response, so no need to simplify. And then the last part, part D, let me use a different color. They tell us the second train travels north from origin station, and its velocity is given by this equation. So what we have is train A that is at a position of 300 at t equals 2, traveling east, and a train B, which is 400 meters north of origin station, traveling north. And it's asking for the distance between, it's asking for how the distance between the two trains is changing. So if I call this side X, this side Y, and this side Z, then the equation that relates those three quantities is Pythagorean theorem, x squared plus y squared equals z squared. And what we're looking for is dz dt. So the way that I would create dz dt is by differentiating with respect to time. Took the derivative of x squared, which is 2x. I just took the derivative of something that's not a t, so then with respect to t, the same with 2y dt. And the same with z squared. And then we could start filling in things that we know. At time t equals 2, x is 300, dx dt from the table at t equals 2 is 100. dx dt is the velocity of A. Plus 2 times y is 400. dy dt at time t equals 2 is going to be given by this equation, v sub b of t. V sub b of 2 is 125. Plugging into v sub b, plugging 2 into v sub b, negative 5 times 4 is going to be negative 20. Negative 20 plus 60 times 2, which is 120. Negative 20 plus 120 makes 100, and then 100 plus 25 makes 125. Equals 2 times z, dz dt. The only thing that should not be filled in for is dz dt. Looking at that triangle, one side's 300, the other side's 400. So then Pythagorean theorem tells me that that hypotenuse must be 500. And then we want to solve for dz dt. dz dt is equal to solve for dz dt, I would just divide both sides by 2 times 500. So 2 times 300 times 100 plus 2 times 400 times 125. All of that divided by 2 times 500. Certainly there are some things we could do to simplify, but this is free response, so there's no need to simplify. The points here, 1 point for the average acceleration, 1 point for the analysis that is this inequality, 1 point for the intermediate value theorem justification, 1 point for an expression function, a position expression, and 1 point for the trapezoidal sum, and 1 point for the approximation of the position at t equals 12, which means that we added the 300 that was the position at time t equals 2. 1 point for the Pythagorean theorem expression differentiated using implicit differentiation, and then 1 point for dz dt. That's the 9 total points.